Longevity science is not just some weird fringe idea anymore. It has exploded out of the shadows and into serious top-tier research labs, pulling in billions of dollars. So today, we're going to dive deep into the core ideas that are fueling this entire revolution. We'll look at why we age and what science is actually doing to change that.
Okay, let's just get right to the heart of it all with the one question that changes everything. Is aging just something that happens to us, this inevitable decline, or is it a biological process that we can actually target and treat just like we would any other disease?
For the longest time, the scientific consensus was pretty solid. Aging is inevitable. It's just decay. But that view is being completely overturned. And it's all because of a powerful new theory about what's really going on inside ourselves as the years go by.
So to really get a handle on this new approach, we have to start with the main framework, the idea that underpins everything we're about to talk about. It's called the information theory of aging, and it's probably the best explanation we have for why we age in the first place.
Now this is where things get really interesting. The old way of thinking was that our DNA, our cellular hardware, just gets damaged over time. It's like metal rusting. It builds up, it's messy, and it's almost impossible to fix. The new theory, which is really championed by guys like David Sinclair at Harvard, says, hold on. The hardware is actually mostly fine. The real problem is with the software, the epigenetic code that tells the hardware what to do. That software gets corrupted. And here's the kicker. Corrupted software? Well, it might just be recoverable.
So what exactly is this software? Well, it's called the epigenome. Think of it this way. If DNA is the computer hardware that's in every single one of your cells, the epigenome is the operating system. It's what tells a liver cell, hey, you're a liver cell, and a brain cell, you're a brain cell. Even though they have the exact same DNA, it gives them their job description. So the crucial question is, what messes up the software? Well, every single day our DNA gets hit with damage, and our cells have to send out a repair crew. But here's the problem. Every time the crew goes out, they don't quite put all the epigenetic furniture back in the exact same spot. After decades of these constant repair jobs, the instructions get scrambled, and cells, they start to forget what they're supposed to be doing. And that cellular confusion, that is what we call aging.
And this right here, this is the most mind-blowingly hopeful part of the entire theory. If the problem is just corrupted information, not destroyed hardware, it means that somewhere in the cell, a backup copy of the original, youthful software probably still exists. We just have to figure out how to access it.
So when this epigenetic software starts to glitch out, what does that actually look like in our bodies? Well, that brings us to the major biological breakdowns, what scientists call the hallmarks of aging. These hallmarks are the real-world consequences of that information loss. You start to see the rise of these senescent zombie cells. You get a state of chronic inflammation just simmering away. A key growth pathway called mTR gets stuck in the on position, and a critical energy molecule, NAD+, starts running on empty. They're all symptoms of that one underlying problem. Let's just focus on this one for a second, because the name alone is just fantastic: zombie cells. As our cells get older and more damaged, some of them are supposed to just die off. But instead, they enter this weird zombie-like state. They stop dividing, but they don't go away quietly. Oh no. They sit there pumping out a nasty cocktail of inflammatory signals that damage all the healthy cells around them. It's a really vicious cycle.
And just look at this number, 50%. That's roughly how much our NAD+ levels drop by the time we hit middle age. And this stuff is absolutely vital for the enzymes that, maintain our epigenome and repair our DNA. It's like trying to run a citywide emergency repair service after your fuel budget has been cut in half. Okay, so if we understand the problems, these hallmarks of aging, what in the world can we actually do about them? This brings us to some of the most exciting interventions that are either available now or are getting really close, and each one targets a specific hallmark.
This table just lays it out so clearly. You've got that mTR growth pathway stuck in overdrive. There are drugs like rapamycin that can tone it down. Need to clear out those zombie cells? You've got compounds called senolytics. And what about that energy crisis? Well, you can use NAD+ precursors to help refill the tank. See, each tool has a very specific job to do.
Now here is a super important detail that most people miss. One of the most studied senolytic combos is dasatinib plus quercetin, or D plus Q. But, and this is a big but, you can't just go grab any bottle of quercetin off the shelf. Standard quercetin is barely absorbed by our bodies. The human trials all use a special phytosome formulation that can boost its bioavailability by up to 20 times. It's a perfect example of how the little details in this field really matter.
So far, we've basically been talking about slowing aging down, hitting the brakes. But what about that backup copy of our youthful information? Let's talk about the absolute cutting edge, the science that isn't just trying to slow the clock, but to actively rewind it. This is where things start to sound like straight-up science fiction, but I promise you, it's real. The idea is called partial reprogramming. Using a set of proteins called Yamanaka factors, scientists can now briefly flip a reset switch inside a cell. The goal is to rewind that epigenetic clock just enough to make the cell young again, without going so far that it completely forgets its identity.
And if you think that sounds far off, just look at this timeline. The speed of progress here is absolutely staggering. In 2006, this was a Nobel Prize-winning discovery in a petri dish. By 2020, it was being used to reverse age-related blindness in mice. Just last year, they showed it works in monkeys, and human trials are set to begin in a couple of years. The pace is just wild.
And you don't have to take my word for it. This quote from that huge 2020 study in the journal Nature says it all. The treatment didn't just make the cells look younger on a test. No, it restored their youthful programming, which in turn restored their actual function. I mean, they literally reversed blindness in old mice. It just shows the incredible power of targeting the information, not just the damage.
Okay, so with all these different ideas floating around, how do we pull it all together into a strategy that actually makes sense? Well, this brings us to the idea of a longevity toolkit, which combines different approaches with one absolutely critical element: measurement.
A really popular approach now is building what's called a stack. That just means combining different interventions that target different aging pathways. So you might use something like rapamycin to keep mTOR in check, take a round of senolytics every now and then to clear out zombie cells, support your NAD+ levels daily, and of course, keep your muscle with resistance training. But that last step, that's the one that ties it all together.
And this is so important because you really can't manage what you don't measure. This isn't just guesswork anymore. We now have these incredibly advanced epigenetic clocks, like one called Dunedin Pace, that can literally measure your biological rate of aging. And these tools are so reliable now that the FDA actually accepts them as endpoints in clinical trials. It's how we're going to know if any of this is actually working.
Which brings us to one last big provocative thought. The gap between cool science in a lab and actual medicine you can get is shrinking faster than ever before. The biology is becoming clearer, the tools are getting better, and AI is speeding up every single step. So the question is no longer if this is going to happen, but how soon? Are we ready for what comes next?